Assalamu alaikum wa rahmatullah. My name is Ammar Ali Fadil. I am master student in communication and computer department. I would like to present my project with the name Self-Coherent Optical Transmission System for Short Haul Communications. My project is under supervised by Dr. Zoraida Bizan. First of all, my project presentation contains project introduction, literature review, research methodology, results and discussion, conclusions, future works with the details. Project introduction. Optical fiber transmission is the most powerful technology for providing fast and inexpensive bandwidth for all data service, including 5G mobile, industrial, and residential internet, cloud computing, and video streaming. Coherent optical technology provides features that enable multiple terabits per second in conjunction with the other optical transmissions such as polarization division multiplexing and dense wavelength division multiplexing (DWDM). The researchers expect coherent detection will be used in short reach, short haul distance since bit rates exceed 400 gigabit per second. The techniques are used in this project include coherent OFDM, self-homodyne coherent detection, polarization division multiplexing, dense wavelength division multiplexing. Coherent OFDM offers many advantages such as large bandwidth and spectral efficiency. Moreover, the coherent OFDM makes the system immune to optical fiber impairments such as chromatic and intersymbol interference. Self-homodyne detection has been proposed to eliminate the existence of the local oscillator laser and expensive DSP, which are typically used in conventional coherent detection system while still providing higher bit rate than conventional direct detection. Polarization division multiplexing is a powerful technique for cost-effective transmission by double up the transmission capacity. The research problems. Coherent short-reach optics have found applications in data center interconnection space, which are considered a key enabling technology for higher data rates. Evolving the higher bit rates combined with the increased baud rate and higher order modulation scheme. The shifting toward coherent optical system may pose more challenge to optical networks, such as increased receiver circuit complexity due to the frequency offset corrections and carrier phase noise compensation. My project aims and objectives are to investigate coherent optical transmission system designs for short haul communication, to design a self-coherent optical transmission system, to analyze the performance of self-coherent optical transmission system for short reach distance. The scope of this project is limited to design coherent OFDM transmitter and receiver that supports several wavelengths based on DWDM and both polarization planes, XY planes, aided by co-propagated narrow line width pilotrons transmitted orthogonally with their optical OFDM signals that use as phase reference instead of using local oscillators or additional complex DSP recovery circuits. Literature review. Transmission networks are subject to unprecedented demands in terms of bandwidth. Bandwidth efficient and cost-effective transmission system must be used to satisfy a variety of characteristics in optical networks, such as flexibility, scalability, and low cost per unit bandwidth. Heavy traffic requires increased capacity in both short and long reach fiber optics networks for optimal service transmission. Coherent optics have significantly improved optical transmission system to replace direct detection, allowing for a widespread upgrade and the new deployment of DWDM networks with data rates reach up to 400 gigabit per second per wavelength or higher. Coherent optics provides several advantages, include coherent optics improves the receiver sensitivity with sufficient local oscillator power to overcome the limitation of the other optical noises like shoot and amplified spontaneous emission noise. Coherent optics provide high spectral efficiency paired with high bit rates per channel using polarization multiplexing to develop channel transmission and as compared with direct detection. Coherent transmission has become the industry standard for high data rate transmission and short haul transmission for data center interconnection to enhance the transmission system capacity along with the use of DWDM network systems. Coherent optical detection. The basic idea behind coherent optical detection is to combine the received signal with another continuous light wave emitted by local oscillator before feeding it into the photodetectors. There are two main types of coherent detection techniques based on how the local oscillator frequency is set relative to the signal frequency. These types are heterodyne and homodyne. And the heterodyne detection, the frequency of the local oscillator is not much the frequency of the received signal. And the homodyne detection, the frequency of the local oscillator is much of the frequency received of the received signal. The heterodyne detection requires an image rejection filter and twice as much as photodetector bandwidth. The homodyne detection requires phase noise cancellation. My project will rely on homodyne detection where I replace the local oscillator with pilot tones to avoid the phase noise compensation complexity at receiver side and frequency shifting to simplify the receiver design the receiver. Coherent optical OFDM has emerged as an efficient technique for high data rate beyond 400 gigabits per second. Coherent OFDM integrates the advantages of the OFDM modulation technique and coherent detection technique and have many benefits that are crucial for future high-speed fiber optic transmission system. These advantages include reduce the effect of the chromatic dispersion and polarization mode dispersion, give high spectral efficiency, improve the receiver sensitivity. The generic coherent OFDM system consists of a radio frequency OFDM coder, radio to optical up converter, optical channel, optical to radio down converter, and finally radio frequency OFDM decoder. There are two types of coherent OFDM architecture. These types are direct up conversion and intermediate frequency architectures. Direct up and down conversion is another synonym of homodyne detection, and intermediate frequency architecture is another synonym of heterodyne detection. The direct detection, that direct conversion architecture eliminates the need of narrow optical bandpass filter in both the transmitter and the receiver as compared with intermediate frequency architecture. This figure clarifies the various methods to send the pilot tones in self-homodyne detection. The first approach is sending pilot tones using dedicated fiber, or called space division multiplexing, as shown in figure A. The second approach is sending pilot tones orthogonally with their modulated signal, or with name polarized division multiplexing, as shown in figure B. The spectral interleaving for self-homodine detection is a useful technique for raising the spectral efficiency of self-homodine polarization division multiplexing system. And this technique, both polarization states are utilized to allow transmission of narrow pilot tones orthogonally with their modulated signals, and among with others to improve spectral efficiency by reducing the wasted in spectral compared with self-homodine polarization division multiplexing, as shown in previous figure B. This slide organized as a table to illustrate some of the techniques that have been used before and that I have benefited from them in my proposal, in my project. So my project consists of combination of these related works, as we can see here. These techniques support higher data rate transmission and with different distance. Research methodology. The proposed project is based on combining the use of self-homodine IPDM interleaved polarization division multiplexing for coherent transmission techniques with optical OFDM and DWDM techniques, and with conjunction with DWDM techniques. This project is designed and simulated using VPI transmission maker. The project is subject to analyze and assess the performance after system optimization measures. By the way, this is not the first time that this topic has been addressed, but I took this project from another side by employing optical OFDM to enhance the bandwidth and spectral efficiency. The proposed scheme for optical transmitter as follows. All the optical signals in order of the WDM spectra, as shown in the previous figure, are linearly polarized on the x-axis, while even signal are on the y-axis. Odd and even pilot tones are then polarized by 90 degrees by using a polarization controller to accompany their modulated signal orthogonally. The interleaved spectra are produced by using a beam combiner, then the output of the transmitter from the WDM IPDM spectrum, as shown in figure previously. This is the VPI scheme for the transmitter. On the receiver side, the IPDM spectra are presented are separated into their respective state of polarization. It's based state of polarization using a beam splitter. Each modulated signal combines its own pilot tones and transmitted to the specified receiver using demultiplexer. Then the orthogonal pilot tones are polarized by 90 degrees to accompany their modulated signal before entering the homodine receiver, as shown in this figure. This scheme of VPI receiver. Finally, a DSP module that is used in this scheme for clock recovery and bit error estimate with scattering plot. This flowchart clarifies the organization of my proposal project, my project. This simulation is done by VPI transmission maker. The process in this flowcharts are choosing subcarrier symbol mapping, including for 163264 QAM. Fiber length, changing the fiber length from back to back to 150 kilometers, changing the DWDM channel spacing from 100 testing DWDM channel spacing for both 100 gigabit per second gigahertz with and 50 gigahertz channel spacing. The benchmark of BER in this project is least than 1 per 1,000, which is least than the standardized forward error correction for coherent detection. As shown in this table, this is the main parameters for OFDM coder and decoder, and also the main parameters of the optical transmitter. In this project, I have used 160 gigabit per second for each per wavelength, and I send the laser source launch power is 0 dBm. This slide shows the optical networks parameters. And primary, I have used 100 kilometers to represent the short reach self-homodynamic coherent detection applications. And then I test my simulation to 150 kilometers to investigate the maximum performance of my project. Results and discussion. I divided the results according to the effect of modulation orders and fiber length. The effect of modulation orders is to evaluate in this project, to evaluate the effect of variation of modulation mapping size on the proposed system. Four modulation orders were selected to evaluate the system performance. The VPI simulator shows the effect of changing modulation mapping size on system performance at distance 100 kilometer with 17 dBm launch power for 150 gigahertz DWDM system. The constellation diagram shown on other slides for the second channel to demonstrate the system reliability in receiving a specific channel that is sandwiched between the two adjacent carriers of the same polarization state. As shown in this figure, here, this is the transmitted and received the DWDM signal for 100 gigahertz channel spacing for 4 QAM and 16 QAM. Also, this slide shows the DWDM signals for transmitters and transmitted and received signal for 32 QAM and 64 QAM for 100 gigahertz channel spacing. This is the constellation diagram for the received signal at 100 kilometer fiber length. At 100 gigahertz channel spacing. This figure shows the four-QAM OFDM orthogonally polarized signal at 50 gigahertz channel spacing. First and figure A showed first and third transmitted signal. Figure B second and fourth transmitted signal. Figure C shows first and third received signals, and finally figure D second and fourth transmitted signals. This figure, as previously slides, shows the DWDM signals for 16 and for transmitted and received signals for 16 and 32 QAM for an 50 gigahertz channel spacing. This figure shows 64. This figure shows the 64 QAM for 50 gigahertz channel spacing. And these constellation diagrams for both modulation, for modulation orders, 4 QAM, 16 QAM, 32 QAM, 64 QAM, for after 100 kilometers for 50 gigahertz channel spacing. The effect of the fiber length. This figure shows simulation results of increasing fiber length on BER as a result of decreasing the received optical power for different MQAM modulation orders for both 100 gigahertz and 50 gigahertz channel spacing, respectively at 17 dPm launch power. The fiber length in this simulation is 150 kilometer to give an overview for maximum system performance. From this figure, the four modulation orders for 16, 32, 64 QAM, and the same DWDM channel spacing, 100 gigahertz, and another figure with 50 gigahertz. To give the best give the best BER, minimum BER performance up to 50 kilometer with minor change, despite the apparent difference in BER between the two DWDM system with the DWDM channel spacing, as shown in this figure. With the same MQAM size. The crosstalk has significant effect when the DWDM gets denser because because of the degradation of the signal to noise compared with the least dense WDM. Even if the impact of the four-wave mixes is ignored. As shown in both figures, the clearest examples of the effect of the crosstalks on receiving symbols before and after the intensification of the WDM spectra. However, the system performance is still good with the specified distance and transmitted power. The proposed system accepts the best performance for 150 gigahertz DWDM channel spacing system up to BER threshold, which is less than the standardized forward error correction for coherent detection, which should be less than -3 log BER. The conclusions. This project describes and presents the results of the comparing the performance of the self-homodine IPDM DWDM based on coherent OFDM for 160 gigabit per second per wavelength. In recent years, coherent OFDM techniques received research attention due to its advantages, as mentioned previously. The proposed system demonstrates maximum acceptable BER over the fiber with the length ranging between 90 and 120 kilometers for 4 modulation orders for both 150 gigahertz channel spacing at 0 dBm laser source per wavelength and 17 dBm length power by erbium doped fiber amplifier to downstream network to send 100 gigabit per second per wavelength, as mentioned previously. The contribution of this work are achieved by designing and developing the DWDM transmission system based on self-homodine coherent OFDM by exploiting both polarization state to fold the transmission capacity and to send pilotons that propagate orthogonally with their modulated signals to be used as a phase reference rather than using a local oscillator or complex DSP for short reach optical communication system. The future works. System performance can be verified and improved through various types of equipment are available in laboratory by hardware experiment. The second future works is implement an optically polarization mode dispersion compensator because the proposed system is sensitive to polarization mode, its polarization dispersion. For mode dispersion for length exceeding the short reach by measuring the polarization mode dispersion for modifying an optical delay line to retard or advanced polarized optical signals. The third future works in my projects is to implement a hybrid WDM time division multiplexing OFDM passive optical network, combining the combination that provides several benefits, including greater dynamic bandwidth allocation, flexibility, high scalability, and reaching distance up of 100 kilometers. This is the references that I have used in my project. Thank you so much.